back as promised. Moment question. We've got a 2D moment problem, right? Find the moment produced at point A by this 500 Newton force on this crazy curved rod here, okay? I'm going to propose to you that there's two ways we can do this, and we're going to do it both ways and see if we don't get the same answer both ways. Way number one, we're going to use the moment at point A is equal to R cross F, okay? We talked about this in the last video. R is a position vector. Do you remember what it is? Tell me. Go ahead. It goes from the point you're taking a moment about to anywhere on the line of action of the force. And then F is nothing more than a 3D force or a 2D force written in vector form, okay? And number two, I'm going to propose to you that we could do it this way, and that is moment is equal to force times distance, okay? So we'll work it both ways and see what happens, okay? So the first thing I want you to do, let's work it this way, is identify what is R, that position vector, okay? Now I'm gonna propose to you that there are two choices here, okay? Because R can be anywhere along the line of action of the force. So R could be from A to here. Okay, that could be one choice, or this could be a choice. Okay, now which one of these do you want to write in vector form, R1 or R2? Man, R1, I could do it, right? But I'm going to have to do some I'm going to have to make a triangle out of this and calculate that height, and I don't know, this is a lot, right? But R2 is just from here to there. It starts at the R vector goes from the point you're taking the moment about to the line of action of the force. And look, this force's line of action goes right through that point. Well, how do you get from here to there? You just go 3 in the x direction. You're there, right? So let's use R2. R2 is equal to 3 I hat. And that's meters. Because the cool thing about a radius is it goes over here and over there and over there, everywhere, right? Okay? And then F. Can you write vector F in Cartesian form? Okay, let's see. Well, here's vector F, okay? So vector F is at a 45-degree angle. And so vector F, in 2D, it's pretty easy to write, right? It's a 500 cos 45 I hat plus 500 sine 45 j hat. Okay? So there's our two vectors. So now what's left? Piece of cake, man. Put it in a matrix, turn the crank. Okay, here we go. And already, right, what do we know? This is a 2D problem, so where's the moment? Always going to be in 2D? Around the k-axis, always around the z-axis. This is an xy problem. The moment is always around k hat. But this will show you that. Okay, I, j, k. Okay, so the moment at A is equal to, and I like to put a little r and a little f there so I don't get those backwards because it's r cross f, not f cross r, because that'll mess everything up. You know what? I need some numbers here, don't I? What is 500 times 0.707? 353.5. I like to have a number instead of all that cosine business in my matrix over here, right? So R is 300, okay? And F is 353.5. 353.5 and 0, right? There is no k hat, right? Okay, here we go. Let's cross this and see what we get. Remember, I hat, cover up the I, and you get 0 minus 0. Cover up the j, and you get 0 minus 0. Cover up the k, and you get 3 times 353.5 minus 0, okay? So 3 times 353.5 is 1060.5. And this is, what is this? This is Newton meters, right? Newton meters. The R was in meters. This guy was in newtons. Went to sleep there for a second, didn't I? So Newton meters, okay? And you'll also notice this. I got a positive answer. So what does that mean? Remember, positive on moments, right? You'll see me write this little symbol a lot. Is a little counterclockwise swirl with a plus in the middle of it, which just is a little note to self that counterclockwise should be positive. So that tells me if I pull on this like that, it's going to rotate this system about point A in a counterclockwise fashion. Do you agree? And if you don't see that, a lot of people have trouble seeing that, right? Let me just extend this line of action. What if I took that force and I moved it right here? Whoop, whoop. Okay? If I'm here and I push, it's a little easier to see, isn't it? That that's going to rotate me counterclockwise, right? That's a good answer. I like that. That was method 1 using R cross F. Let's see what method 2 does, okay? Let's see what method 2 does. Now, the only difference for method 2, I'm not going to use this matrix, so I'm going to get rid of that. All right, and I don't need all this equation that I had down here, okay? So method 2 is just force times distance, but what I do need to do is take that guy and break him into 2 components, okay? So he's got one here, and he's got one here. Okay, this guy is 500 cos 45, and this is 500 sine 45. Okay. Whoo! Okay, let's see. I need this right here, and I need this right here. These 2 distances. I got to have that, right? Now, since that's a 45-degree triangle, I know these 2 distances are the same. As a matter of fact, this hypotenuse right here has to be 3, doesn't it? It's a radius, right? So, you know what that distance is? It's clear. 3 times 0.707. 2.12. So this side's 2.12. This side's 2.12. Okay, so here we go. Let's use this equation number 2. The moment. Let's just do this. The sum of the moments about point A is equal to this being positive, okay? And let's see what we got, okay? So put my finger at point A. First one I'm going to do is this guy, okay? And he is going to rotate me which way? Rotate me, because when you're doing moments, right, you got to ask yourself 2 questions. Number 1, which way does he make me spin? Clockwise or counterclockwise, because that tells me the sign. And number 2, how far away is it? That's the only 2 questions you need to ask. So, which way does he make me spin? If I push up, it's going to make me spin counterclockwise. That's positive. So 500 sine 45, okay, times how far away. And here's a silly song I'll sing to you. Ready? If the force is in the X, then the distance in the Y. If the force is in the Y, then the distance in the X. Okay, so don't make me sing that song again. Okay, ever again. Okay, so because, right, the distance has to be, for the moment, for this equation, the distance has to be perpendicular. So if I have a Y force, the distance needs to be in the X direction. If I have an X force, the distance needs to be in the Y direction. Okay, so we're doing this guy. He's in the Y, so what's the distance? The distance is from point A to this line of action, which is 5.12. Okay? All right, that got that one. Check. And then the next one is that guy. Which way does he make me spin? I put my finger here. Because this guy is above, right? Just think of him being over here. Right? Which way would he make me spin? Clockwise. That guy's going to be negative. So minus 500 cosine 45 times how far away? All right. Well, the force is in the X, so the distance in the 2.12. Okay. Let's see what we get. I'm so excited. 500 times 0.707 equals 353.5. times 5.12 equals 1809.9. Okay, this up here, 1809.9. This down here is 500 times 0.707 times 2.12 equals 749.4. So let's see, that guy was negative. So 1809.9 minus answer equals 1060.48. We'll call it 1060.5. Okay, guess what? Same thing, same thing. So two different methods to work the same problem. Now me personally, dude, I am going to go to this method every time. That matrix thing has a lot of opportunity for sign mess ups. And besides that, this just has one force. If I had 5 forces on here and I've got to add up all of those and do the moments, I got to do 5 matrix and then add the result from those matrix. I got to add those together. That's horrible. Whereas this, I just sum up all 5 in one equation. Sum them up. What's that one? Which ways do you make me spin? How far away? Which ways do you make me spin? How far away, right? This is way easier. So you're going to see me go to this for 2D problems all the time. I'll use R cross F for 3D problems because it handles 3D vectors really nicely. But for 2D, dude, I'm going to method number 2 every time. Okay, I hope that helps, and I'll see you in the next video.